Six. Well, thanks everyone for coming. Today we have a guest from the University of Groningen, Johannes Miocic. He will be talking about the effect of heterogeneity in different aspects of related to the geological storage of geofluids. Sorry.
No worries.
No.
Keep going. Okay.
So Johannes is associate lecturer at the University of Groningen, and we've been working together for a few years now. And he's been here. He has been here for the last 3 days on a research visit, and I think he can introduce himself.
Yeah, I'll do that.
Thanks.
Yeah. Okay. Hello, everyone. Thank you very much for inviting me to talk to you here and to come here, and also people online. It's the first time I'm being live streamed, so it's very exciting for me. Yeah, so I'm from the Netherlands, and you can see that also. Okay, so now this is work. No, it is, and you can also see it very well, I think, here on my title slide. It's a very typical Dutch landscape. You have a windmill and you have a farm. And what I want to talk to you about today is the impact of geological heterogeneity on production-induced compaction of the Groningen field. It's a very long title. And so basically, I want to talk a little bit about geological heterogeneity, mainly from a sedimentological point of view, and compaction, so geomechanics, how these two are linked together. The research I'm presenting to you is funded by the DeepNL. Here, the DeepNL program, which is a big program funded by the Dutch Research Organization. And the money which funds that comes from NUM, which is the operator of the Groningen gas field, but it's funneled through the governmental organization to ensure that people trust what we have to say, so that we're not directly financed by the NUM. And let's have a look why we need to look at compaction if we think about depleted gas fields. Think about porous media. Here you can see a sandstone with sand grains in gray, and the pore space, very simplified here, filled in green. And at initial reservoir pressure, before you start any production or injection in a porous media, you can see that the overburden load, which is all the mass of the rocks above, are equally distributed between the grains and the gas filling, the pore filling fluid, in this case, gas. Now, if you start producing some of that fluid, what happens is that the pressure is being reduced. So the gas or the pore fluid is not able to take up all of that load anymore. And especially where grains touch, you can see that indicated in red, compaction occurs. So that the grains start slipping or breaking, and this can lead to reservoir compaction. And for example, in the case of the Groningen field, where the reservoir itself is about 150 meters thick, we have a reservoir compaction of 30 to 60 centimeters. So this can be quite significant if you talk about thicker reservoirs. Now, this is an important aspect, and it's not only important if you think about production from a gas field, but if you think about future uses of the subsurface, this stays to be an important aspect. Because if you think about cyclic use of the subsurface, so when we pressurize the subsurface, when we, for example, want to store hydrogen or CO2 or air or heat, if we think about cyclic pressure changes, then this is a process which occurs several times per year, that you fluctuate the reservoir pressure, and this can then also lead to compaction in those reservoirs. So it's very important that we understand what processes governs the compaction of this porous media, so that we can predict it and ensure that future subsurface utilizations are done in a safe manner. And of course, then the question is, okay, what kind of mechanisms could control the way that our reservoir compacts? And I'm, of course, not the first one to think of this. Many others have thought about this. And the interesting thing is that the composition of your rock obviously would play a role. It's very different if you have only quartz grains, various spheres, or compared to real reservoirs where you have different shapes of grains, but also cements and different types of grains. So what you can see here is on the right side, an example from a Dutch group who has looked into the role of clay minerals in these sandstones. So here you have a sand grain in the center, and you can see it's surrounded by these red things, which are clay films, which surround individual grains. And what they have postulated is that if you have clay films, they act like a soap, kind of like as a lubricant, and then the grains can easier rearrange during reservoir compaction. And that means if you have more of these clays, you would have more compaction in the end. So that's interesting, but it's very theoretical. And so the goal of my research that I want to show you today is more, what does this actually look like in the real world, in the reservoir? Can we see changes in clays and reservoir composition in heterogeneity? So what controls then this variability that we may observe in the field? And does this heterogeneity in a real reservoir actually also impact the mechanical behavior? So, it could be that we observe very different sandstones, some with more clay minerals, some with other type of cement. But in the end, it doesn't have any effect on how strongly those sands compact. And then that would mean we have a nice study of somebody looking at rocks, but for the real world, it doesn't actually have any impact. So that is something that I want to discuss in the second half of my talk. So let's go to the Groningen gas field. You can see a map here. It is the 11th biggest gas field in the world. It's Europe's biggest gas field. It's located in the northeastern part of the Netherlands. And it has produced a lot of gas since the early 60s. You can see here, this is a top reservoir map. You can see it's located around 3,000 to 3,500 meters depth. And you can see already also a lot of black lines, which are faults, which are very common in this reservoir. And production started in the early 60s. You can see here on this graph where you have in blue the production of gas. In red, you can see bars which indicate induced seismicity. So this field was closed 2023, even though it holds still a lot of gas. And the reason for that is this induced seismicity. So because we have reservoir compaction, and this compaction isn't the same throughout the reservoir, but where you have faults, across faults, you may get differential compaction, and this then can lead to induced seismicity. And you can see this has happened since at least the early 90s. There's indications that even the decades before that, induced seismicity occurred, but because there was no monitoring, this wasn't observed. You can see there is an earthquake here with a magnitude of around 3 in 2017. That's a bit nicer to see here on the map, where you can see in green the outline of the reservoir and the red dots induced seismicity events. And you can see the biggest one has 3.6. Now, if you're from an area where there's natural seismicity, you're like, 3.6, it's nothing to worry about. You may be correct if your houses are built to withstand seismicity. But in this area, there is no natural seismic hazard at all. So the buildings are not built to withstand earthquakes. And the earthquakes are very shallow. They're only in 3 kilometers depth compared to natural seismicity, which may occur in tens of kilometers depth. And that also the top 500 meters of the Dutch subsurface are only made up of, I'm going to call it mixture of water, sand, and mud. So when it starts shaking, it's not the best. And that then leads to a lot of damages on houses. You can see here, there's a crack going right through here, this typical Dutch house with the red bricks. And this has led to quite some societal and political effects in the region. People felt that they were not informed properly, that there wasn't done enough to stop the earthquakes, and that they weren't getting enough money to repair their houses. So overall, a very interesting field site to study. As a geologist, this is a really cool site to study because there's a wealth of data. So they have drilled over 200 wells in that area, of which about 90 have cores. There's seismic data available. It's onshore, so it's a bit poor, but there's lots of data to look at. One final comment on this slide here, you can see on the map here, in black lines, subsidence contours indicated, and you can see at the center of the field, this is in centimeters. We have currently, or 10 years ago when this map was done, 30 centimeters of subsidence. And even though they close the field, the pressure will recalibrate in the field, and it's predicted that subsidence will be 50 to 60 centimeters by 2060. Now, this also, if you live in Barcelona, doesn't sound too bad, maybe. But if you live like my house, 20 centimeters above sea level, this is a bit of an issue if suddenly you're under sea level. So also one more reason to look into what controls the subsidence and compaction on a reservoir scale. This here is a cross-section, basically north-south through the field, and you can see the field is hosted in Groningen, so Permian age sandstone, and they're overlain by a thinnish claystone layer and very thick salt layer. So you have roughly 1 kilometer of salt on top of the reservoir, and this forms the main seal. You can also see that the reservoir thins from south thickens from south to north. So here in the south, you only have 80-meter thickness, while in the north, you have up to 200 meters of reservoir. And that is related to the depositional setting in the sedimentary basin at the time when it was forming. It was formed in the southern Permian Basin. Maybe some of you have heard of that name, which was a big sedimentary basin spanning basically from west from the UK to east to Poland, or today where Poland is. And it was forming north of the Variscan mountain front. So you had mountain front in the south, and north of that you had a big basin in which you have to imagine it's a very arid basin. It was a continental climate, very dry, not a lot of precipitation. And in the center of this basin, you had a salt pond forming where, due to evaporation from groundwater, salt has been formed. And around the salt basin, you have rivers or ephemeral rivers bringing material from the mountains into the basin. I always find it's very hard to see on a map. So let's have a look at a 3D imagination how the landscape looked back then. So you have these alluvial fans coming out of the mountains, bringing material into the basin. And in the basin, you have wind then reworking these deposits. You can see the further, so if you think from a geological perspective and think about grain size, you would expect a very clear grain size trend from the alluvial fan to the playa in the center, which is something to keep in mind for later. Something which you can see here also is that apparently this playa lake expanded every now and then. So this could be related to climatic changes. Maybe there were a couple of tens of thousands of years where there was more rain. Or it could also just show that people don't really understand the system yet. So they make these wiggles to show that there's some changes, which could be related to this depositional environment, but could also be related to other factors. Models are nice, but I think looking at the rocks, how this actually looks like, also gives a much better impression. So you can see if you go from the right to the left, we basically go from the basin margin to the basin center. We have relatively coarse conglomeratic sandstones moving into more finer fraction and low aeolian sandstones to more mud flats on the left side. And so obviously the reservoir rocks are more the ones on the right side. So you can see here these sandstones, these relatively fine-grained sandstones, have a relatively high porosity. So the reservoir has, on average, about 18 to 25%, which is quite good for a rock that old. And of course, in the more playa and the more conglomeratic rocks, you do have lower porosities and then also lower permeabilities. And we wanted to understand how this rock composition changes throughout the field. And for that, Sebastian, so you can see here, a PhD student of mine, he looked at many hundreds thin sections, mainly from all of these from many wells. And you can see I'm very important. I'm telling him what to do, as any good supervisor would do. He looked at 17 wells throughout the field, and you can see here where they're located. And first I want to show you, okay, how does sedimentology change? If you look at these different wells, it is just as you would expect from all the story that I've told you so far. If you go from the south to the north and you look at grain sizes, you can see darker colors represent coarser grain sizes. If you go from the south to the north, you become finer because you move towards the basin center. So not very surprising. And if you look at the depositional setting, which is also a reflection of the grain size, or the other way around, the grain size is a reflection of the depositional setting, you can also see that more reddish colors decrease while more purplish colors increase. So we move away from, or we get more distal the further we go to the north. But you can see there is quite some heterogeneity. So it's not just one constant change, but it sometimes goes up and down a little bit. And basically in every well, you can find every depositional environment and every grain size. So if you pick a certain well, you can say the probability that it has a certain amount of a grain size, but you can't say it will not have a certain grain size, which shows you there's quite some heterogeneity in this system. Sebastian looked a lot at the diagenesis and the role of clays, because this has something which has been postulated to play a bigger role when we talk about compaction. And I just want to show you a couple of nice images, because I think that's sometimes quite nice. So you can see here in SEM images, and you can see these grains, and you can see these clay cutons, which really kind of like surround the whole grains. Here on top, there is none, probably because of the way this was prepared. But you can also see clays which actually fill the spaces between grains. So you can see here these nice clay platelets, and similar down here as well. So there's different types of clays, but predominantly, as we expected, there's a lot of these cutons around the individual grains. We also find a lot of later processes. So these cutons, they formed very early on, right after the sand grains were deposited. But here you can see the remnants of a grain. So you can see the grain cuton, these clays, they're still here. But the actual feldspar grain, which used to be there, has been dissolved. And instead you have formed quartz cements and some of these other clay minerals. And this is something that we see very commonly. And this is also one reason why these sands still have a very good porosity, because we have a lot of these dissolved grains, which then, of course, are very good because you can fill those with fluids. Now, there's a lot of these processes. I don't want to go through all of them. And just want to show you there is quite a few of clays. So the first, you can see 1, 2, 3, 4, 5, 6 of these processes or phases. They're all clays. So there's a lot of clays involved. But I think very importantly, we also do have dolomite, which is more a cement, which forms massively very early on and very strongly cements your sands. So you don't actually have any porosity left. All of these phases are found in nearly all samples. And if you think about, okay, so how can we analyze this? This is quite an unconventional way. This is a correspondence analysis of the different phases here. So we have the different clay minerals, and the color of the dots represents where you find these samples, where yellow is north and more purple is south, and green is kind of like in the middle. And what you can see is that certain clay minerals you mainly find in northern wells, so chlorite, halite, smectite, and illite, while kaolinite you find mainly in the south. And dolomite kind of like is present in all colors, is present in all phases, in all wells. So that's quite interesting. So that if you think about these clay minerals, which can have some impact or are postulated to have some impact on compactional behavior, there seems to be some clear north-south difference here. If we think look a little bit closer at dolomite, which seems to occur in all samples or in all areas, it also occurs in all depositional environments. So if you think about dolomite, it starts forming due to evaporation of groundwater very early on. It also occurs in all facies, so it's also not a very good indicator. So dolomite is very heterogeneous, and we're still trying to understand it a little bit better. What really governs this? We have a model, which I really don't want to go into detail, which we can now use to predict where in the field we will find what type of cement, where we find more kaolinite in the south, for example. So this is this area here. And we were able to link the geological history of our field with these different diagenetic phases. So we do have a relatively good understanding of where and how these occur, kind of like better understanding the composition and heterogeneity of our samples. And we're trying to make this even better on a smaller scale by using shortwave infrared spectroscopy, where we scan our core slabs using a camera which picks up spectra of the shortwave infrared wavelengths. You can see here wavelengths. You get a reflectance spectra for pixel sizes of 200 by 200 microns. And if you analyze these spectra, you can then identify, okay, which minerals are present in your sample. And then you can go from a core photo to, for example, a carbonate content. And then you can see it's very heterogeneous also on very small scales, so that you have layers which have very high carbonate content quite closely linked to layers which have nearly no carbonate content. So that makes it for me very interesting. How can we ever be able to predict something like this? So we need to think about maybe a bit larger scale to try to predict these different types of cements. Now, very nice story, understanding diagenesis and where you can find what kind of cement. For some people, that's maybe boring. Now, because the real question really is, how does that impact compaction? So how do we understand how the different cementation or different composition of our rocks impact compaction? My title was compaction, so let's go back to that. For that, what we did is we chose 4 different samples, which kind of like have end-member compositions. One of them has mainly one type of clays, the other one has other types of clays. One of them has more different cements. You can see them here with different colors. And if I talk about we, then of course it's not me. That was Dimitri here, has done triaxial deformation experiments, because we want to understand the compactional behavior. So what we do is we take these samples, put them into a triaxial deformation apparatus, which was done at the University of Utrecht. And based on the composition of these samples, we would expect that they behave differently if we compact them, based on, for example, their composition. So you can see here, for these clays, we would expect that they compact relatively large, while if we have very strongly cemented samples, we would expect that they deform relatively low. So let's see what we actually get. So you can see here, cumulative and elastic strain. So that's how much compaction do we observe in these samples against the different differential stresses. And what you can see here, that we have light blue, which is a sample where we expected low, so that's good. Then we have blue and pinkish, where we say, okay, medium and high. So they're changed in the order, but generally what we expect, they're higher than light blue. But what you can see is that this yellow one is very different. We expected this should be low deformation, but we actually see very high deformation. And that's, of course, not what we expected, which makes it very interesting, because whenever there's something which you don't expect, it's quite fun to figure it out. Now, if you look into the sample in more detail, what you can actually see is that the cementation is very much layer-based, similar to what we've seen on the shortwave infrared photo, where you have every couple of millimeters a high or low carbonate content. This is what you observe here in the thin section as well. So you can see some layers are very strongly cemented and others are more porous. And what we try to understand at the moment is how does this layering actually impact compactional behavior? And what we do for that is we map cracks. So we have scanned these samples, or we have thin sections of these samples before and after deformation. And what Dimitri has done, he has mapped grains on these images, thousands of grains in many hours, and can then show where do these cracks occur in those samples. So what we here have is now some rows diagrams. So if you look at all cracks in the undeformed versus deformed sample, you can see good data, thank God. Our samples have more cracks after we deformed them. So that's a good sign that if we do deform our samples, there's cracks forming. So that means that if we look where those cracks occur, that may also help. If you look just at the grains, you can see there is cracks forming in the grains more as well. So you can see before in the undeformed sample, the orientation of the cracks in grains was relatively random, but you can see that after our deformation experiments, the cracks in grains have more deformation, or cracks in grains are more aligned with the stress that we put in them during the experiments. And the same is also true for the cement, but you can see there's a clear difference between the cracks in our deformed samples in grains and the cements when it comes to orientation. So that seems to us to indicate that the orientation, that the cements and grains behave differently during the deformation experiments, and that they pick up stress or strain in a different way. We're still trying to map this out, but what we think is that if we have cement right at the boundary between uncemented and cemented layers, that this is where we get the highest amount of strain and then also the highest amount of cracks in our cement. Hopefully we will be able to see that in a couple of weeks. So what should we have seen so far, or what should you have learned? You've seen there is a lot of sedimentary and diagenetic heterogeneity in the Groningen field. And this actually is not something really new for the road ligand, but this was the first time somebody looked at this in high detail. Here you can see a very nice example of what that means if we have heterogeneity in our rocks when it comes to fluid flow properties. You can see here, this is a road ligand outcrop in Germany. You can see different colors, different species, but what you can also see, water is only coming out of this very thin layer here, so that this is the preferential flow path. And if you want to have a good reservoir model, you need to understand where these high porosity layers are and what their properties are. I hopefully have also shown you that we now better understand the heterogeneity of the field, where it occurs, what type of cements and what type of grains we find where. And the next steps that we're going to do is that we're going to use the information that we have on the field-wide scale, couple them together with the results of the geomechanical experiments, and we'll try to implement that in compactional models for the whole field. Very simplified models in 2D, not in 3D, but to see if we include that heterogeneity, we can improve the compactional prediction of the field. I think you've also seen that heterogeneity really occurs on a millimeter or micrometer scale in these reservoirs, and that is something which is common for many reservoirs. And if you want to understand or predict heterogeneity, you really need to think from very small to quite large scales. And in this case here, if you want to predict reservoir compaction. So that was me talking about the impact of geological heterogeneity on compaction in the Groningen field, and I'm happy to take any questions if there are any. I hope there are.
Thank you, Johannes, for a very interesting talk. I don't know if there's any questions in the audience. Yeah. So,
Yeah, Johannes, thank you. So the gas fields are often seen as the perfect storage sites for, well, either for cyclic storage, as you said, or for like CO2 as like energy units. You showed, like, when you presented the design principle and showed the outcome of this, basically the compaction of the reservoir. So when we analyze these depleted fields, we usually look at core data or violin data or whatever, which were taken at the beginning of the production operation. So how dissimilar is what we see at the beginning of production of a field, like when we take these values then to our storage operation, our analysis of the storage operation? What would you suggest a different permeability, porosity, and other properties that you have?
So I think porosity and permeability will not change that much. So even if you have here, you know, the compaction over 200 meters is 60 centimeters, so maybe you have a 0.5% less porosity overall, but it doesn't affect that much. But what really affects is if you want to understand compactional behavior, it matters if you take a sample which was drilled at the very start of the field, or if you take a sample which is towards the end of the lifetime, because then it will already have seen this compaction behavior over the lifetime of the field. That's actually a problem we have as well. So when I showed you the 4 samples that we use for the triaxial deformation experiments, they come from 3 wells of different years. So 2 of them are very early on from the mid 60s, but one of them is from the 80s. And we think that some of the differences that we see in the behavior may also actually be linked to that history of compaction that we already also see. And if you think about reusing these sites for storage, for compaction, it would be very good to fill it with something again. Nobody's going to do that in the Groningen case because you need very large volumes, and any earthquake which would then be generated or would occur later on, there would be a liability issue. Is it going to be from the original production or from the injection? But when it comes to reservoir stability, increasing the pore fluid pressure again would be, I think, better than leaving it as it is.
But the compaction itself is not reversed.
No, but so the compaction partially is reversible. So the inelastic strain, I think, is about 30%. But the elastic strain is 60 to 70%, and that you can reverse. So if you up the pressure to original or a bit less than original fluid pressure, you could reverse some of that compaction.
I have a question regarding diagenesis. So
yeah.
What is controlling this heterogeneity of dolomite cement, so that you have it in some laminae or small layers and not in other parts? Is it because there are seeds for dolomite precipitation there, or I mean, what's the reason?
Yeah, if I only knew. So I can only that's something which we try to figure out. So most of the dolomite precipitation occurs very early on. And so it has to do with groundwater fluctuation shortly after the deposition. So it will be controlled slightly by facies. So if you're in a very Aeolian dune setting, you will not have groundwater fluctuation because the groundwater will be lower, and there you would not have that much dolomite cementation. If you're in these below the or in the groundwater area where groundwater level changes and you have evaporation and dolomite cement forms, our idea is at the moment that preferential flow paths, where you have high permeability and porosity for more water to flow through to evaporate, that this is where you start dolomite precipitation, and then it just continues because you have a starting point for these minerals to form. But you've seen it's very heterogeneous. grain size plays a little bit a role as well. So there's lots of factors going into that.
And clay content or
Yeah, clay content as well, a little bit. So if you have, actually for dolomite, not so much. So for quartz, for example, if you have a clay cutin, it prohibits quartz precipitation. So that's something we can clearly see. But the clay content really doesn't control that much where dolomite occurs.
Yeah, I'm surprised you mentioned that there is no change or not obvious change in the porosity and permeability
Yep.
properties. I guess my question is whether are you going to try to quantify that somehow, and whether that lack of change is also heterogeneous, and you will have some places where the change is none, versus some places where there's a massive change. Because I guess if you are rotating grains and you are at some point you will never be able to recover the original structure. We see that in some other regions where even by burial compaction you lose the original.
So what we did is we measured porosity before and after our deformation experiments, and there the change was not significant. So was within the measurement errors. So I don't think that is something that you would expect to see. Also because when you rotate a grain, you free some space as well. So I don't think that you will have that much of change in porosity. What I think is more likely is that you would see a change in permeability, because what can happen is that some of these clay cutins are then smushed into pore throats, and then you would have smaller permeabilities. But that's not something that our data shows so far.
But like the fact that you have, or you could have 60 centimeters.
Yeah.
I mean, that alone is a proof that you're reducing the product now, because where are those 60
Yeah.
centimeters?
But if you think about it, the reservoir is 200 meters thick. And then
One more question.
can you first?
Thank you very much for the talk. It was very nice and very interesting. I wonder if you have thought how to translate this study to the operations. So, for instance, if you identify areas that can deal much better with the compaction, you will focus the production in those areas. But then I wonder if at the end you have a pressure decline in the reservoir can migrate to other areas, neighboring areas. So I wonder how.
Yeah. That's a very, very interesting question. So first of all, they stop production and they will not produce again due to the societal and political issues coming with it. So they close the field. But that would be a good idea if we were able to identify, areas where you have less risk of compaction. You could do that. However, what we see now that they close compaction, there is pressure communication throughout the field, so it would recalibrate again the pressure. Yeah. So then also in more compaction prone areas, you would have a drop in for pressure.
Yeah. Coming back to this as a storage, because the root-ligand, the repeat root-ligand things in the southern North Sea are targets for gas storage. You mentioned the earthquakes here due to the loss of pressure. Is there any indication for leakage?
No.
To these earthquakes?
No. So leak, because you have 1 kilometer of salt on top, we don't see any indications of leakage. I could imagine that maybe some gas filtrates a little bit into the overlaying claystone, but I don't think you see any large scale indications of leakage.
So it's quite good. It's quite a good message.
Yeah, I guess. Yeah. Also, I think there is gas storage operations already in some of these road-ligand fields, and they also have some induced seismicity, but I also don't know of any indications that there is leakage.
I think that's it. Thank you so much.
Thank you all.